Hello Hassam. So this is going to be my presentation for the third chapter of the book, Computer Systems. It's about machine or a program representation in machines. So let's get right into it. First of all, I would like to start by congratulating you on your previous framing of the book. I have just started to get the feel of the book, and I guess your idea is very correct. Indeed, the main problem is that abstraction hides complexity, but they also hide behavior, and that hidden behavior creates a knowledge asymmetry that might lead to problems. But what I'm going to add is that there are maybe two layers of the knowledge asymmetry. There is the first layer, which is failure mode, ghost model, implicit assumptions, and these are generally learned by bumping into them. Like, for example, you run a program and you get a bug, and in the process of fixing the bug, you realize that there is an extra step to use set function or set the abstraction of any certain language. But the second layer, which are errors, this is my what I'm going to add, is that there are center errors that are based on certain philosophical mismatches between how reality works and how we have been able to represent reality in the machine. And these are very dangerous because they don't give you a signal. For example, you have a hanging byte, an overflow, and you don't get an error. Perhaps your code might work fine, but there is always this potential failure point that it could explode at any moment, provided certain conditions that are not going to be always available come out. And the key problem with these is that you can't really rely on bumping into them. You can't really rely on experience to learn the various failures that come with the fact abstraction hide complexity, and they also hide behavior, because it's luck based. You can just never in your career have the chance to program certain functions that tell you that there is this sort of problem you need to know. So there must be a problem, and I believe this is the main message of the book, and that there is already a specific behavior at the machine level, and this behavior is abstracted from you, is hidden away from you in order to make you more productive. But there are certain mistakes that you might fall into, and just relying on chance to bump into these mistakes and then learning that they exist is not a reliable way of learning. And it is therefore important to understand the behavior at the machine level, and use that to infer any potential holes in whatever future program you're going to write. And this is essentially the main idea of the book. I believe it is definitely the main idea, the main pattern that I saw in this chapter, because the book kept on going about various uses. It compiles C code into assembly code, and it kind of analyzes the assembly code and tries to infer certain problems, and these problems are then given as revelations about how you can use set functionalities in the future. And once again, there may be certain differences in future chapters, but I believe this is the main idea of the book, is that there is a certain mismatch between the abstraction and the machine level code, or the machine level shape of said abstraction. By abstraction in this case I mean language and the various options it allows you. And in order to prevent, or in order to be able to write good code, functional code, you must also invest time in learning about the specific machine shape of the language you're using, or any other form of abstraction, in order to be able to tell what potential problems you might have in the future. And once again, I'm just because I can't just say that in this presentation and just move on, and I also can't just explain the assembly code in the chapter. You can do that on your own. You're going to be much more effective of grappling with it on your own. But what I'm going to do is I'm going to give a certain model or certain blueprint about how to read the chapter. First of all, you must understand that all languages, in this case, these are the main abstraction we are dealing with, C in specific, and that all abstractions or all languages have a specific shape at the machine level. and you must understand this shape. And how to do that? You first of all you must study the machine. For example, in the case of C, you just compile it and you read the assembly output. In other languages that are based on interpreters, whatever, you must figure out what that is. And then you must also hone your mathematical skill, and specifically your complexity scale. Not your ability to determine the big O notation, but your ability to write proofs for algorithms. And you must use that to kind of infer the range of possible outcomes for the machine level code, and use that in order to bound your implementation of the abstraction for the language you're using. And I'm just now going to give some examples, or kind of what I learned from this chapter, which goes through this method that I just explained for C. So let's get into it. The first of all is the illusion of variables, because in the mind of programmer, a variable is, a named thing, like x is x, but in reality x is not x. X is an illusion that is very convenient and very useful for you when you're in the high level. And C also counts as high level here, when you're in the high level of programming and trying to program. But in the machine code, which is what matters actually, it is not an actual location, it is simply a location policy. So if you ask your C program where is variable x, your C program is going to give you an answer. But if you ask the machine where is x, it does not know where x is. X can be at the stack, x can be at a register, x can be in wherever it is, just going to retrieve it. So variables, even though they're named, are location policy, it's not an actual location. I'm going to give an example of how this can show up in your code. It's not a very apparent example, but maybe the next example will be more apparent. But essentially, you have two C variables with different names, but they can also map to the same memory. This is very important, because you could have two variables that are sharing a byte, or sharing a certain part of a byte or whatever, and in your mind there are two different variables. God knows how it works, but if you know how it works, there is a certain level of danger, because this can be effectively the same slots in the memory. The next possible problem with the abstraction is the idea of pointers, and specifically in the case of arrays. In C, an array is essentially a pointer to the head of a contiguous list of memory slots. So if in your mind array, this notation means that there is a container with walls, that's not true. It just means that there is a contiguous set of memory slots, and that your array points to the top. And when you run a command like array-i or array brackets I, this what essentially the machine does is it executes pointer plus I by 8 if you're using integer. It could be more if you're using something else. But this is what I'm sorry, I'm laughing because this seems to me like it's very basic to say, and maybe I'm just talking nonsense, but this is actually very important. Your machine is going to execute the pointer, in this case it's array, plus I multiplied by the size in bytes of the type of I, or of the type of the array. And this means that your actual array is not a container with walls, but rather it is the first of a sequence, and this can lead to many other problems. The book then goes on to talk about various other problems. I'm not going to mention them really, because this can be done much more effectively at home. If I'm just going to read the book for you, you're better reading it on your own, because you can reread and read at your own pace. But it goes about conditions, and about how when you execute a condition you have various flags that are being modified under the hood. It talks about loops and control flow, and specifically the switch statement, which has a jump table, and this jump table can cause various issues, various security issues, because even though the switch is faster as a loop, as a control flow mechanism, but it also has a jump table, and if somebody achieves or can inject location, it can cause your program to jump to various parts and give access to things that it should not give access to. You have procedures, which are essentially they push an index, they jump to a location, then they pop from the stack and then jump in this sequence there are many other flows or many other possible injections that can happen. The stack buffer, which is also it's the same issue with the same issue as we mentioned about the pointers, because it's not an actual buffer. It is pointing to the head of a sequence. And just the main takeaway is that there is always going to be a mismatch between the shape of the machine design of an abstraction and the abstraction above it, whatever it may be. Even C is considered above. Even C, which is in the mind of programmers a low level language, is also above the machine. And you cannot solve these abstraction problems because there is no issue. The mismatch is structural and it's very expensive to eliminate. And what you should do instead is rather try to work around it. You should adopt a policy of managing consequences rather than trying to eliminate the cost. And this gets me to what I believe is a useful way to frame this. Beyond the chapter's content of the various issues in C, or various issues you can derive from studying the machine code after you compile a C program, is that there is a structural gap between the machine and every abstraction built above it. This applies to any abstraction, C, Python, whatever. And the gap is not a bug; it is simply the price of abstraction. This should be clear. You should not waste your time trying to eliminate the abstraction, because you can't. And specifically, that after 50 years we have a whole infrastructure built around these gaps. And you should also understand that the rate at which experience, meaning you code and you get a bug, and you kind of discover that there is an issue, is too slow and too luck-based. You can go your entire career without discovering that there is a potential issue with the if statement or whatever. And so you must have a working construct or a working mental model of the shape of the abstraction you are using, and you have to constantly run it against your usage of set abstraction, meaning your language. You have to constantly run your construct or your mental model of the shape of the machine against your mental model of the abstraction of the language, and try to infer what are the possible problems by whatever usage you're doing right now, and then update your code. This has been my take on this chapter, or rather my take on the book, because this chapter really opened up the book for me. But yeah, this is it, and I'm going to see you next week.